This is Dr. Holt. In this video I want to talk primarily about impulse, but before I start I want to work one problem dealing with the conservation of linear momentum, and then I will get into the impulse lecture.
Okay, let's look over this problem. We have a 5 kilogram object and a 10 kilogram object, both resting on a frictionless table. So the key word here is that it's resting. Since it's resting here, we can say P initial of the system must equal to 0. Okay, then the spring is released and the objects fly off in opposite directions. The 5 kilogram object has a velocity of 8 meters per second to the left. What is the velocity of the 10 kilogram object? Alright, the easiest thing to do on these would be to go ahead and set yourself up some type of coordinate system. So we'll set up a coordinate system here, and we'll say that anything that goes to the left will be negative, anything that goes to the right will be positive. We can go ahead and draw a vector going this way. We'll just draw a little some type of mass here. Let's say we'll pick okay, so we'll have that be our 5 kilogram object. Has a velocity of 8 meters a second to the left. And now what will be the velocity of the 10? Well, the 10 has got to go the opposite direction. Make a little circle like this. We'll move it back into place here so they line up, and we'll go ahead and draw our vector going to the right. No, not very good there. Let's do that a little better than that. Going to the maybe. Here we go, going to the right. And then we'll label everything. And then this problem should fall apart. So we have a 10 kilogram object. And this will be the velocity of the 10 kilogram object. So we know our PI is equal to 0. Then we know immediately that PF, our final momentum of the system, must equal to 0. So we just set this problem up as 5 times minus 8 plus 10 times V10 must equal to 0 minus 40. We'll move the 10 over. And we solve for V10. And we can find out the velocity it must go would be 4 meters a second. Pretty simple. And again, this one will go to the right because the summation of those have to equal 0. Alright, let's go ahead and move forward. During the collision, the only significant forces are always going to be the internal interaction forces, which are always going to be equal and opposite. Meaning that when a bug hits your windshield with a certain force, the windshield will push back with exactly the same magnitude of the force but in opposite direction. As a result, we can say that momentum is conserved, meaning that the total momentum of the system the instant before the collision is equal to the total momentum the instant following the collision. When two objects collide, they usually exert very large forces on one another for a very short period of time. The force exerted by a baseball bat on a ball, for example, may be several thousand times the weight of the ball, but this enormous force exerted for only a millisecond or so. Such forces are sometimes called impulse or impulsive forces. The mathematical definition of impulse is going to be the integral between the initial time of impact to the final time of impact of force times dt. So basically, the integral, the impulse is going to be the area under the curve between ti and tf of f dt. And we can say that the net impulse is going to always be the change in momentum. And then when we're talking about a system itself, the impulse momentum theorem for a system, then the net external impulse is always going to be the integral between ti of tf of force net external dt, or again, the change in momentum of the system. Okay, if we look at a graph between force and time, then this area under the curve between here is the definition of impulse. When we go back to calculus, so we remember that the average force, we could say the average force can be defined as 1 over Tf minus Ti of the integral of f dt, of this being Ti and this being Tf. So when we calculate the average, all we're really trying to do is to say then the average force during the time of the impact between Ti and Tf would be this distance here. If we multiply this distance here by the distance between Tf minus Ti, we really get the area under the curve. So what we're saying is we can calculate the average force during a collision. My recommendation as far as a strategy to use when trying to solve collision type problems would be first to calculate the impulse and delta t. Usually you're going to be given enough information you'll be able to do this. The second thing I'm going to recommend is that, and I did this earlier in this presentation, is always draw a sketch. Draw a sketch of what's taking place before and after the position of the object. This will help you to visualize what's taking place, and then calculate the change of momentum. What was the initial momentum of the system and what was the final momentum of the system? And then you can use your kinematic equations, possibly if necessary, to estimate the collision time. And then by definition, we know that force times delta t is always going to equal to the change in my momentum or the impulse. So from this we can always calculate the force, or we can calculate delta t, or we can calculate the impulse, knowing, because all we need to know is two of these, and we can calculate the other one. Let's look at a problem here. Let me change back to another pen. Excuse me. Here you have a 0.3 kilogram brick. It's going to be dropped from a height of 8 meters. It hits the ground and comes to rest. What is the impulse exerted by the ground on the brick during the collision? If it takes 0.0013 seconds from the time the brick first touches the ground until it comes to rest, what is the average force exerted by the ground on the brick? Alright, this starts out as a kinematic equation because we have height here. So if we draw kind of what a picture would look like, we're just dropping a brick. I'll just draw this as a brick. And we're dropping it from here to here, with this being 8 meters. So we go back and we know from kinematic equations, can we not say that Vf squared is going to equal to Vi squared minus 2 times 9.8 times the distance that we let it fall, which would be 8. If we do this, and since we're going falling, we're going, well, we can leave it this way. We'll just leave it this way. It really doesn't matter. I'll make it negative because we're falling negative. So now if I take the velocity here and I calculate the velocity, I can find that Vf squared is equal to 156.8. So then when I take the square root, obviously I'm going to get plus or minus, when I do a square root, of 12.52. Excuse me. And since I know that the brick is traveling down here, we'll just draw this as a vector. Can I not say it's going to be 12.52? It's going to be going down. So now I have my velocity. So now let's go ahead and let's calculate what the momentum is going to be. We know that the initial momentum, now this is initial momentum at impact, is going to be equal to the mass of the brick. So we said 0.30 kilograms times the velocity, and we'll make that 12.52. We'll make that negative because I'm coming down, and that's going to give me a value of negative 3.76 kilograms. Make sure your units are always in kilograms, times meters per second. Okay, so that's my initial momentum. Okay, now we know that the brick is going to come to a stop. So can we not say that Pf here is got to be 0 because I have no velocity? So let's figure out what the change momentum would be. Delta P, the change momentum, is always going to equal to Pf minus pi. If I do that, we could say that the change momentum here would be 3.76 kilograms times meters per second. Alright, so now we know that force times time is equal to impulse. And we know impulse is equal to the change momentum. So we can say that our force is equal to, sorry, let me erase that. Force times time. Can I not say my force times my time, which was given 0.0013, must equal to my change momentum, or my impulse, which is 3.76. All we have to do is solve for F, and F would equal to 2,890 newtons. Alright, so this part here would be what they asked me for, was in part B. If it takes the time, what is the average force? So this would be the average force, and we could make that average too. So this would be part B. Now to go back to A, it says what is the impulse? Again, impulse is change momentum, so my impulse would be 3.76 kilograms times meters per second. A relatively pretty straightforward problem. Let's look at this problem here, and we can draw a picture on this one. We have a 0.15 kilogram baseball traveling horizontally. It's hit by a bat, and its direction is exactly reversed. So velocity changes from 20 to negative 20. So let's just grab a small circle. So we really, this is what we're going to have initially. Oh, not very good. Let me draw that vector a little straighter. Boy, I can draw that better than that, I hope. Okay, let's go ahead and label that. Now this is my mass. It's going to be 0.15 kilograms. I'm going 20 meters a second. Okay, so we're going to draw, we'll do like an initial. So can we not say that pi here, my initial momentum, would equal to 0.15 times the velocity of the baseball, and we're going to say anything goes to the right would be positive, and when I do that, that's going to give me 3 kilograms times meters per second. Alright, so we'll say this is before impact. Okay, now it's hit by a bat. Now the baseball is going to reverse itself. So let's just grab this baseball, and we'll move one over here. Now the baseball is going to be going back the opposite direction. And now since it's going the opposite direction, we're going to make it minus 20. Again, you need to set up some type of axis system so you can be consistent about this. So PF here is going to be, again, the mass of the baseball, but I'm going to multiply it by negative 20. And when I do that, I'm going to get negative 3 kilograms times meters per second. Alright, so now let's find out what the change momentum would be. Can we not say that the change in momentum, which is also equal to impulse, is going to equal to my final minus my initial, which is going to give me minus 6 kilograms times meters per second. So this value right here is the impulse delivered by the bat to the ball. Now it says that the baseball is in contact with a bat for 1.3 milliseconds. What is the average force? Again, that we remember that force times delta t is always equal to impulse or change momentum. So we're just going to set this up. We have force. We go ahead and multiply it by our time, which is going to be 1.3, and that's milliseconds times 10 minus 3. We set that equal to negative 6 kilograms times meters per second. We go ahead and calculate the force, and the force in this case would be 4,650 newtons, and now we know that's going to a left because this is going to give us a negative value here. So we can just draw that as a vector going back that direction, which makes sense. If the bat is hitting the ball with 4,650 newtons to the left at impact, then we would expect the ball to reverse directions. Alright, I hope you found this video useful on how to calculate impulse and collisions.